you actually make use of the DC compared to AC. But the funny thing is this one is actually three-phase DE. So you must produce a three-phase from the DC. Okay? So you have a three-phase inverter, right? Remember the three-phase inverter, you have three functions. They have fixed power electronic switches, switching in a certain sequence. Right? You must have a fixed sequence, then you produce look a line sine wave. But that sine wave is pretty poor because it's considered stacked. You know terrace, you been to Malaysia, right? Those terrace paddy field. Stack, right? So it's something like that. It's stack to constitute almost like a sine wave, but it's not exactly a sine wave. So by theory of this Fourier analysis is any periodic waveform. You break it down into small constituent, you can have a lot of sine wave, perfect sine wave, but at different frequency, alright? Different frequency. And you combine them, then you'll get, but the one with the most dominant will be the one with fundamental. Okay? Fundamental is the most dominant. Then followed by third harmonic, fifth harmonic, all harmonic, or even harmonic, depending on it. So here what happened is, we are going to convert from your normal AC, 50 Hz, just drive the induction motor, depends on frequency, right? It's only one speed. Or change a little bit, the speed, change a little bit, but cannot change much. So you really want to change the speed of the induction motor, you must what? Change the frequency. So that's why they cannot go directly from AC 50 Hz to drive the motor, alright? For variable speed drive, AC. They have to convert to DC, then DC convert back to AC again. But this is DC to AC using a converter, electronically driven, can change the frequency. Okay? Got it? So that's the reason why somebody say, hey, why AC, come back AC, what's the problem? Right? AC, give it AC, why is so complicated? So it's AC, change to DC, DC, and change back to AC. But the output AC with variable voltage, variable frequency, VVVF. Okay? Got it? Okay. So now what we are going to have is, we have this box, we just going to build it because it's too complicated. Alright? Okay. So we bought this from the industry. It can be used to drive, I think, up to 10, I think it's 10 kilowatts or what. Very powerful, right? Induction motor. So this one here, we bought the controller from, now it's absorbed, makan by Amazon already. What's the name? Control Technique. The Control Technique?
Control Technique.
Company drive, the drive.
Unidrive.
Unidrive.
M700.
Okay, so they makan them, they take over. So we are still around, but they are gone already. Okay, so we are using this one. We build a box, then we bring out all the controls. That means the controls are supposed to connect to at the back. A lot of those connectors, all these. We bring it to the front to become knobs or switches, so that it's easy for you to see. All right. Okay, so now what happened is now you can don't crowd around. You can see. Now the other group are here. You can speak louder. Come, just sit around. Take a seat. But don't sit on the chair, please. Don't sit on the table. Okay, so the objective is to show that the speed of induction motor, AC motor, is proportional to the frequency of the supply. Remember? Yeah, what's the formula? NS equals to, NS equals to 120 F over DE. Alright? Okay, remember? The induction motor is running at a speed which is very close to the rotating field. Rotating field speed is called synchronous speed, NS. You are governed by the formula. Hello? Okay? Alright, so now what happened is, you also study from that, you need to use VOF control, right? VOF control so that you can have rated torque at almost any speed, below rated speed. If you don't use VOF control at certain speed, the motor becomes saturated, then become very hot, you can't realize the torque you want. At very low speed, you cannot realize the torque. So you control VOF constant all along, then you're able to produce the required torque you want at any speed. Alright? So to observe the operation of the AC induction motor under the following control scheme, VOF, alright, and also this is for speed below rated speed, below rated speed. Then the other, once it goes to above rated speed, which could happen, sometimes you want to run slightly above rated speed, then you switch over to a different type of control mechanism we call constant terminal voltage control. The terminal voltage is fixed, cannot go up anymore because it's rated voltage, but the frequency can still increase. You can run faster, but the torque will be suffer. You will not be able to output the rated torque anymore. Okay? Right, so there's a trade-off. Hello, are you all with me? Yeah. Okay. So now very simple connection now. This blue box has all this here. Then internally they have a rectifier to convert AC input here, single phase AC, come out 3-phase AC, variable frequency, variable voltage. Alright? That makes you the variable AC drive. So the AC motor is also there, the blue one. And this one is connected as a star configuration. Sorry about your 3-phase theory, the motor theory, as we acquire add-on information during our course because it's supposed to be covered next semester, right? But don't worry, you put your effort, not wasted, because next semester you have easier time once you go to the machine, because you have a very good idea what's happening. All right. Okay, so these are 3 lines coming out, 3-phase, but the voltage and current, voltage and frequency can vary. Through where? Through here. This knob controls the torque. This knob controls enable this AC drive. This one can bring forward or backward drive. All right. Then this one can change the speed. So the speed and torque controlled by these 2 knobs. Then you switch from AC single phase or 3-phase. That means the input can be a 3-phase also. Can also be single phase. But for convenience, we switch to 1-phase. 1-phase. Line neutral. And so from here, you can actually change the frequency by changing the speed here. All right. You change the frequency by turning a knob. Then you find that it will change the speed. Okay. Then what we want you to measure is over here. At different frequency, what is the corresponding voltage and the speed? All right. You'll notice that VOF occurs below the 50 Hz, which is the rated one. After that, this one will have a constant voltage. All right. The frequency go up, but the voltage remains the same. But the speed will be going up all the time, until maximum up to 80 Hz. So your motor can be made to run at 80 Hz, very fast. All right. Almost more than double the speed. Not double, 100 is double. Okay. All right. Then what you need to do is you set all these settings here. Initial setting, forward, reverse, selector put to forward, torque knob put to about 5, speed knob put to about 1, power input selection put to single phase. Then you enable it, then you start to turn the speed knob to increase the frequency. All right. So for each of these readings here, very easy. You just need to do a measurement of measure the phase voltage. In fact, the voltage you use a voltmeter. All right, you use a voltmeter, put here AC voltmeter for one of the phase. Then you measure each time you change the frequency. You measure the voltage, the speed. Don't need to use tachometer here. This one uses a microcontroller internally. So on the display there will be, I think, 2 lines. 2 lines of LCD display, character display, alphanumeric, which will also show the frequency and the speed. So no need to use tacho. So you just have to switch on, connect properly, switch on, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 reading, I think. About 10, 11 reading, so that is done, right? So after it's done with this one, then they want you to plot this one. You want to plot the results based on this one, study the behavior. Plot the graph of frequency and against motor speed. So this and this. So you have this one. Frequency against speed, and then one graph. Then plot the graph and comment on the relationship, how it looks like. Oh. Plot the graph of the V phase against frequency. So another one will be here. V phase against frequency. Alright. Then plot, then comment. What's the trend? Is it linear or hyperbolic or whatever? Are the three-phase output voltages of the inverter sinusoidal? How do you know? Over there, I think they want you to actually look at the waveform, because if you look at this one, you can see that this one is see, you put one probe here, right? In fact, you have 3 channels, luxurious, so you can put 3 channels. You can see the three waveforms that is seen on the lecture with Dr. Zhu, the online lecture, right? Remember? So there are 3. You can see that there are steps. Right? They're not exactly sine wave, but they are phase shifted 180 degrees to trick the motor into believing that it's 3-phase. Okay, you can see that on the scope. So if you want to see a 3-phase, then you put 3 channel. This one put one channel. The common is neutral, right? Start point. So 1 channel, 2 channel, 3 channel. You put 3 channel. All the 3, 1 U, V, W, right? Put 1 at W. You see all the 3 phases there. All very beautiful, colorful. And don't forget, you have to use the what? Differential probe, because the voltage is quite high. Alright, so differential probe, 3 channels. Draw here.
Set to what? 200.
200 will do, times 200. Differential voltage probe. All these must do differential voltage probe. Then you have to put a DC voltmeter here to measure the V. V you will measure. Then what else you have to measure? The speed. You look at the box here. Is that here the LCD? LCD display. You have the speed. Speed is given. Frequency is given. 2 of them. Just record these 2. And then you turn this. Record. Turn this. Record. Finish very fast. You can finish it within 30 minutes. Okay, so that is the setup. Can you connect this? Don't turn on yet. I will see everything in order. Mr. Lee and you will check. Then you turn on. Finish it, then